I caught up with recently minted Dr. Andrea Stevens of the University of British Columbia to discuss her published paper in the journal on resource concentration by insects and resulting implications for plants. Could you briefly introduce yourself?
Yeah, I'm Andrea Stevens, and I've just recently defended my PhD in zoology at UBC. I'm interested in insect-host plant interactions, in particular in relation to biological control.
So, what problem was your study trying to solve, or what motivated your study?
So in nature, we see that plants are distributed in different patches, and there's been a lot of research looking at thinking about why insects might distribute themselves in different patches. So you see some patches that have large numbers of insects and some that have small numbers of insects. And one of the key hypotheses is that this could be driven by the density of the plants, and different number of insects is driven by the different densities of plants. And so while people have considered why insects might distribute themselves differently, we were interested in what effect that has on the plants.
So, for the uninitiated, can you explain the difference between the resource concentration and resource dilution hypotheses?
The resource concentration is one way that which insects can distribute themselves on plants. And this is sort of the classic ideas put forward by Richard Root in the 1970s. He suggested that insects should distribute themselves on larger patches of the plant. So on each plant, in a big patch, there should be more insects per unit plant, so per leaf, than there are in smaller patches. So not just absolute numbers more, but relative numbers are more in larger patches. Whereas resource dilution is kind of the opposite. So often people have found that there are actually more insects per unit plant in smaller patches. And so relative abundance is higher in these smaller patches. And so that was what we were really interested in. Do these different patterns matter for the plant populations?
What was your main finding or findings of the modeling component of your study?
It was a relatively simple model. Insects just distribute themselves in relation to the plant patches. And we found that if insects were distributed in directly proportional patterns, the plant populations went extinct faster. The greater the variance between the different plant patch sizes, between the different distributions, greater the variance in insect load between the different plant patches, the slower the plant populations went extinct. And so therefore, this suggests that for biological control, we really would like things that distribute themselves in direct proportion, or not far off it to the plant patch sizes.
Could you explain what you found in the field component?
So in the field, we decided, well, let's go out and see if this actually occurs in nature. We have a system here in British Columbia with diffuse snapweed. A ton of insects introduced for control of this species. And the final species that was introduced, Larinus minutus, has been a successful control agent. So we decided to compare the distributions of Larinus minutus to another insect, Urophora affinis, a little fly. And we found that, the fly was unsuccessful in controlling diffuse snapweed. And as we predicted from our model, Larinus minutus followed a directly proportional pattern. Insect load per unit plant was exactly the same regardless of plant density, whereas Urophora affinis followed a resource concentration pattern. The resource concentration pattern led to greater persistence of the plant populations, which might be one reason why Urophora affinis had no effect on knapweed populations. There are probably others as well, almost certainly others as well.
So you suggested that differences in the rates of plant population declines can have community-level implications. I was wondering if you could just go into that a little more, or explain it to the listeners.
So if the plant community is going to respond in different ways. If rates of population decline are slower, we're likely to see different plant species coming in than if they're faster. We also found that the resource concentration led to greater persistence of the plant populations, which obviously is going to have a community level effect. The weed is still there in high abundance, which of course means that nothing else is coming in. So we're going to see, the different distribution of the insects is going to affect the population of their host plant. Because it affects the population of their host plant, it's going to have an effect on the other plants in the community as the plants have competitive interactions with each other.
So you suggested your study has implications for weed biocontrol. Can you explain this?
Weed biocontrol would be ideal to get a biocontrol agent that brings down that plant population as fast as possible. Ideally, you'd like the plant to go locally extinct. You're not going to get extinction on a wider level. But the faster we can bring down that plant population, is really good. And so something that brings it down fast is going to be beneficial. So that's going to be something that responds to plant density in a directly proportional pattern.
So I wonder if you have a sense for how herbivores are distributed across patches in nature. I imagine the answer is it probably depends. But is there any sense for, is there a most common case in nature?
It seems to depend. There's a whole bunch of things that it depends on. And early study, mid-90s, by William Kunin has discussed some of these different things that lead to the different patterns. More recently, a group from out of Stockholm, Peter Hambach's group, has suggested that things that respond, most species are either directly proportional or have a weak resource dilution. And they attribute this to sort of the stitch finding behavior, the plant patch finding behaviors of the insect.
So how general do you think the results from your study are? In what cases would you expect the same or different patterns?
I think the results of the model are likely to be fairly general. Any plant that occurs in a patchy distribution is likely to have these sort of effects. In our model, we assume that the plants could reduce plant populations, and we know that not all insects will reduce plant populations. And that's probably entirely regardless of pattern.
So, for the modeling component, do you think you're going to explore more, different types of parameters or different parameter space or anything?
What I'd really like to do is to move the model out to a community level. So if we have a community of plants, say 6 species of plants, all of them are specialist herbivore, do we get more alpha diversity in patches if all the species in the community follow a resource concentration pattern, which is what I would expect, but we might get greater beta diversity if they all follow a directly proportional pattern. So I'd be really interested to tease apart what happens more at a community level.
So what do you think are the consequences for the fields of this paper?
I think we really need to get a better understanding, and particularly for weed biological control, of when and how and why insects damage plants and we can reduce plant populations. Because for biological control, we've had a lot of successes, but we've also had a lot of failures. And any trait of an insect that we can identify that might make it a good biocontrol agent will be really beneficial. We can go out, we can test this in the native range and say, these are the traits we're looking for. So this is one trait that goes towards that. It also comes back into the general theory of plant persistence, why we get so many biodiversity, maintenance of plant communities.
What do you think was the most challenging part of the study?
I think the most challenging part of the study, just to balance the model, we sort of started thinking of it as a diffuse snapweed model and then sort of broadened it out. But just getting that balance between realism and tractability was the thing I found most challenging when building the model.
And was the field work easy, or was that difficult?
The direct field work itself was relatively straightforward, but bringing the plants back into the lab and we had to dissect out the seed heads to identify the insect load, and that was long and fairly tedious.
So do you have any interesting stories from the field or the lab from this study?
Well, we thought we'd do a third field site, my field assistant and I, and we went out and we started to work on it, but we ended up actually there were a lot of rattlesnakes, surprisingly. Despite it being a fairly rare species, we heard rattlesnakes all around us. And so we had, coming from a country which has no snakes, it was a little bit terrifying. My field assistant refused to work there.